I don't know if 25 minutes I will take.
Okay, so our next speaker is Souvik Pal, and he's going to speak on Harishchandra module over full toroidal Lie algebras and higher dimensional Virasoro algebra.
Thank you, sir, for the introduction. So first of all, I would like to thank the organizers for giving me this wonderful opportunity to present my work here. So today, it's evident from my title, I will be talking about Harishchandra modules over full toroidal Lie algebras and higher dimensional Virasoro. So let me start by motivating all these terms that are there in my title. Okay. So there is this Witt algebra which can be geometrically realized as a Lie algebra of all complex polynomial vector fields on the unit circle. But it also has a very simple algebraic description, that it's an infinite dimensional simple Lie algebra which is Z graded, and this is the Lie algebra structure. So very simple minded way. But although this geometric definition is there is a nice connection with algebra by this classical object called the derivations of the lower polynomial algebra. So this is actually isomorphic, and one can actually show that this is actually a free module of rank 1 over this lower polynomial algebra generated by this L0. Okay, so then this admits a one-dimensional central extension, and this actually gives rise to the Virasoro algebra. This is in fact the universal central extension. So more precisely, this is the Virasoro algebra. So you have this one-dimensional central extension. Here the bracket operation is essentially the same, but here the twist is coming from some cocycle on this W1. And of course, since it's central extension, the K commutes with everything. Okay, now this Virasoro algebra acts on almost every highest weight module for the affine Lie algebra, and this is the Segal-Sugawara construction, and this motivated the construction of the so-called affine Virasoro algebra, which let me now describe. So G is a finite dimensional simple Lie algebra, everything is over C for me, and then we know that it admits of a symmetric non-degenerate and associative or G invariant bilinear form, which is the Killian form given by this prescription. And then the affine Virasoro algebra can be defined in the following way. So this first two terms is sort of the affine Lie algebra, and the next two terms is sort of the Virasoro algebra. We just fuse them together, that's it. And here the bracket operation here is this. Here also there is some cocycle coming here, and this is the Killing form of x and y, and this is the Kronecker delta. Yeah, and K is in the center. The center of the Lie algebra is just K. Okay, so one thing to note that if you take for example L0 here and also L0 here, you will say that this affine Lie algebra is diagonalizable under the L0 action. So you can break it up like this into eigenspaces with respect to this L0. Okay. And this directly gives rise to the triangular decomposition, very natural triangular decomposition. So in the positive, so negative, positive and 0. On the positive I am just correcting the positive graded components and just summing them up. Similarly for the negative, and in the 0 I just have this thing. Okay. So here for the triangular decomposition I am essentially using the well ordering on Z. Is a nice order. Okay, so let me move on to the representation theory part. So what type of representations are we interested in? So for that let us look at the definition of a character. So recall that the character is nothing, it's some gadget, it just keeps track of the eigenspaces and their corresponding dimensions. So where this is the decomposition and this is the eigenspaces with respect to L0. So now for this formula to make sense actually, I need the module to have some eigenspace decomposition with respect to L0 and also these dimensions to be finite, otherwise this formula doesn't make sense. So this is precisely the definition of a Harishchandra module. So you can have a module over the Virasoro or the affine Virasoro. So this is the eigenspace decomposition and all the eigenspaces are finite dimensional. Okay. And so as we have this definition, let us look for some examples of such modules. So these were already there in the literature. These are by Kaplansky and Santharobin. So this is just a basis indexed by Z. So you can just identify it as CTT inverse at this moment at the vector space level, and then you can define the action like this. Example, if you take note that if you take L0 again here, it is acting diagonally here. And the center I am declaring it to be acting trivially. So essentially it's a representation of a W1 really. Okay, and it was shown actually by them that it is irreducible precisely when this condition is holding. And also this, we have this isomorphism T alpha beta and T alpha 0. So okay, so we have this, and another important thing to note about these modules are, if you look at the dimensions of these eigenspaces of these modules, they are one dimensional. Okay, so they are sort of what we call uniformly bounded modules, or this type of modules came up in the talks in the morning also. So these are multiplicity 1, maximum multiplicity is 1 here. So, but there are other classes of modules which we know actually, which occur, which have finite dimensional weight spaces, but they are not bounded. And these are highest or lowest weight modules. So as I said, the Virasoro has a nice triangular decomposition like this. So now, so what we do, we play the usual game. You take an irreducible module over the middle part of the triangular decomposition. It's an abelian Lie algebra. So it will be one dimensional. And let L0 act on it by A and K act on it by B. And we declare the positive part to be acting trivially. And so now you consider the Verma module like you always do by this induction functor. And then we know it will have a unique irreducible quotient. So these modules are the irreducible highest weight modules over the Virasoro. And actually we can do a similar thing by replacing this positive part by the negative part, and do the same thing, and these are called the irreducible lowest weight modules. We don't really care much about them because actually they can be also realized as highest weight modules twisted by this automorphism. Okay. So it was conjectured by Kacs actually in 1982 that all the irreducible Harish-Chandra modules over the Virasoro are either those ones coming from the Kaplansky-Santharobin modules or the highest or lowest weight modules. And this is essentially what was proved by Matthew in 1992, that it is exactly Kacs' conjecture that he proved. So what I want to do actually, so I want to develop this theory in the higher dimensional setup and study the questions that were asked by Kacs. So that is the idea. So let's start with this. So I want to define the higher dimensional for loop algebra. So you take the multi-loop algebra. You replace it by the Laura polynomial algebra in n+1 variable, and you can, it's a Lie algebra of course, in a very simple minded way. And this is my multi-index notation. And so now what should we do? We should take the universal central extension. That is the idea, what we use for affine Lie algebra. So here also we do the same. For that we consider this module of differentials of an+1. So this is the module. This has another nice description which I will tell in the next slide. And you take this differential map like this, which is, and you take, and then the image of this map is given by this. And then you have to look at the quotient. Okay. So these complex terms you don't have to remember, you just remember there is some Zn+1. But the important thing that was proved by Kessel, that this L hat G is the universal central extension of Lg, but the Zn+1 is infinite dimensional except n equal to 0. That means except in the one variable case, this universal central extension part is infinite dimensional. So that is completely different to what happens in the one variable case. Okay, so for, as I said, then for one variable case you get this thing, you just one dimensional central extension, and this is actually the affine Lie algebra associated to G. Okay, so let me try to generalize this Virasoro algebra. So instead of taking of CTT inverse, you take n+1 variable again. Then again one can show that this is actually a free module of rank n+1 generated by these elements. And in fact it is isomorphic to a Lie algebra of complex polynomial vector fields on the torus, n+1 dimensional torus. So now what one should try to do to construct a Virasoro, one should try to take the central extension and get the Virasoro. So by the way, this thing has also a simple Lie algebra, and this is called the higher rank Witt algebra given by this bracket operation. So now as I said, one should naturally try to take the central extension and get the Virasoro, but here is the first problem. Coming from the physicists, they said that this is always centrally closed unless you are in the one variable case. So you never have central extensions in this case unless you are in the one variable setup. So this then Ishwar Rao and Moody proved that although this is always centrally closed, it admits of a non-trivial abelian extension. And the good thing about this is the same abelian extension that appeared for the universal central extension for the multi-loop algebra. And as I said, this is infinite dimensional unless you are in the one variable case. So this again admits two cocycles. So the precise form of the cocycles is not important, but their values is in this Zn plus 1, that infinite dimensional center. These are the cocycles, so it is not important. So just take any arbitrary combination of these cocycles, and now I am ready to define my higher dimensional Virasoro algebra like this. So this is the higher dimensional Virasoro. One thing to note that like this whole Zn plus 1 is not in the center of the Virasoro. Only the k0 to kn, these are only lie in the center. So the center of this Lie algebra is really small, given by n plus 1 elements. But this is very big compared. It's a Zn plus 1 graded Lie algebra. Okay, now I can do the construction corresponding to the affine Virasoro algebra in the higher dimensional setup by just taking this loop and this thing. So this part is sort of the higher dimensional setup for affine, and this is the higher dimensional Virasoro. That is what I did. And again, the thing is that the center here is also very small, given by these ki's. So that is one major difference with the one dimensional setup. And of course there L0 was playing the role of abelian diagonalizable subalgebra. So here d0 to dn, here it is Zn plus 1 graded. So you need n plus 1 operators to to give the to get the diagonalizable subalgebra. Okay. So now what type of problems I was doing actually? So as I said, so here I can also define the notion of the Harishchandra module like this. So that means it's a direct sum of eigenspaces and all the eigenspaces are finite dimensional. Okay. So again I want to make a definition. So a Harishchandra module is uniformly bounded if the eigenspaces are bounded by a fixed constant. Okay. And so the problems that one can ask here is the following. So one can ask that can you classify the irreducible Harishchandra modules over this higher rank Witt algebra or the higher dimensional Virasoro or this full toroidal Lie algebra. So this one has been recently resolved. So I was doing these two things mainly. So now we have this definition. Let us look at some examples of these Harishchandra modules. Okay. So you take a finite dimensional G module, and we know finite dimensional G modules are uniquely determined by a dominant integral weight of G. So this is that lambda 1, and a finite dimensional irreducible GLN plus 1 module. They are determined by a dominant integral weight of SLN plus 1 and a complex number which is the action on the center. So this is these are the two parameters. So now you take their tensor product, this finite dimensional irreducible G module and the finite dimensional irreducible GLN plus 1 module, and tensor it with AN plus 1. And then you can make it a tau n plus 1 module under this action. So this is the action. So here x tensor t power m. So x dot v1, here I am using the fact that this thing is a G module. And here I am declaring that on the Zn plus 1 the action is trivial. And on the derivation, I am also this action I am using the fact that this V2 is a GLN plus 1 module. So this is the action. And what I observed that unless if lambda 1 is not equal to 0, that simply means that this V lambda 1 is not the trivial G module. This module is always irreducible. Okay. This module is always irreducible. And it is clear that the eigenspaces are also uniformly bounded, and the uniform bound is given by this quantity. Okay. And now one can ask what happens when lambda 1 equal to 0. So when lambda 1 equal to 0, so I put 0. So this is not necessarily irreducible, and these are popularly known as Shane-Larsen modules in the literature. So then In 1996 actually, Ishwar Rao investigated when these modules will be irreducible. So this as I said, this part is coming from the G part, so it is 0. So this is irreducible. If this is not very surprising, it is similar to what was there in the one variable setup, but this is the main thing actually. The omega k is the fundamental weight of SLN plus 1. So if you remember actually in the one variable case, what happened actually, so for these modules actually it is, if you put 0, this is in fact V lambda 2 tensor an plus 1. If you take n equal to 0, like in the one variable case, so you are ending up with a GL1 module, so just C. So then, and here it is just A1, so that is just CTT inverse. So that is what we exactly saw for the Kaplansky-Santha-Robin modules. So there was no semi-simple part for there, like GLN has that semi-simple part, SLN plus 1. So this is irreducible if these two conditions are satisfied. And he actually explicitly found out what are the irreducible quotients and the Jordan-Holder series, everything. And this paper was sort of the starting point of a big program related to this classification problem. So then in 2016, Billig and Tony proved that these are exactly the only irreducible uniformly bounded modules over Wn plus 1. Okay. So now when I started to look at these problems actually, so I started with Vir. So remember, Vir was Wn plus 1 direct sum Zn plus 1, that infinite dimensional abelian extension, and this thing was like you tensor G tensor an plus 1 direct sum Zn plus 1 direct sum Wn plus 1. So if V is an irreducible uniformly bounded module over this, then this infinite dimensional, that extension always acts trivially on V. So this was the first non-trivial step. So since we have this, so it is clear then the irreducible uniformly bounded module over the higher dimensional Virasoro will be from the above, because the higher dimensional Virasoro was nothing but Zn plus 1 direct sum Wn plus 1. Okay, so the modules over Vir were classified by due to this. So now for tau n plus 1, one has to work a bit more harder, and one gets actually this thing. So it is exactly what I have defined, V lambda 1 direct sum tensor V lambda 2 tensor an plus 1, and here you note that I am taking non-zero thing, okay, because as I said, if lambda 1 not equal to 0, that module is always irreducible, so I am taking the non-zero thing. And the other one is those uniformly bounded irreducible Wn plus 1 modules, what we just saw. Okay. So another lemma that was really useful for me is that in this category of uniformly bounded modules, these modules always have a finite Jordan-Holder series. It always has a finite length. So that was really the key lemma actually in my paper. Okay. So now that is all about uniformly bounded modules. So we saw in Matthews' theorem there was something called highest weight modules there. Okay. So we should try to imitate what should be the correct notion of highest weight modules. What are the analogs over highest weight modules over this? So if you recall, we defined highest weight modules using a triangular decomposition, and that triangular decomposition essentially used the well ordering on Z. But the main problem actually in the higher dimension, there is no natural ordering on Z, Zn plus 1. Okay. So what we do actually, so we took the Z grading on by eigenvalues of that D naught. So how are you partitioning this Z2 is actually like this. So I am declaring the second quadrant and third quadrant to be my negative part, and my y-axis to be my 0 part, and first quadrant and fourth quadrant to be my positive part. So that is how I am decomposing Z2, and then I get the triangular decomposition. So you see for T naught actually, this is an plus, so this actually ensures that the T naught power is always positive. Similarly for here, and in the negative part, this ensures that the T naught power is always negative. And in the middle part, we don't get that 0 part at all, and we start only from T1 because it is a 0 part. Okay. Okay. So one notable thing is that the middle part is actually this full toroidal algebra in n variables, not n plus 1 variable, but plus 2 copies of an. Okay. and it can be shown that K naught and D naught belongs to the center of this middle part. Okay, these are the two central elements. Okay. So now we play the usual game. You start with an irreducible module over the middle part of the triangular decomposition and declare in the positive part it is 0, and then do the Verma module construction, similar induced module construction, and then one can show that it has a unique irreducible quotient. And this is not important, it is just GLN acts on by automorphisms, like what we saw that lowest weight modules can be realized by twisting the highest weight modules by an automorphism. So similarly here also. So this also gives rise to an irreducible module. So these modules are called modules of the highest weight type. And similarly, it can be defined for Wn plus 1 or Vir by simply dropping the loop part G tensor An plus 1. So one of the difficulties with such problems actually, so in the one variable case, the Verma module always have finite dimensional weight spaces. But in the higher dimensional setup, even if we start with a irreducible Harishchandra module or even uniformly bounded module, you are not guaranteed to have finite dimensional weight spaces for Mx. So you can't conclude that Lx will be a Harishchandra module. So that is one of the prominent difficulties. So the theorem here is that if you start with an irreducible Harishchandra module over tau n plus 1 or over the higher dimensional Virasoro, which is not uniformly bounded, then V is isomorphic to these highest weight type modules. Okay. And X is an irreducible uniformly bounded module. This uniformly bounded is there. But as I said, the classification is still not complete, because even if we start with an irreducible uniformly bounded module X over this middle part of the triangular decomposition, it does not guarantee that finally when you take this induced module and go to the irreducible quotient, it will have finite dimensional weight spaces. So what I need to do to complete the classification, I need to find necessary and sufficient conditions on this X such that Lx will be a Harishchandra module. Oh. So that is what we do actually. So let Lx be an irreducible where, so as I said, K naught and D naught both acts by scalars since it lies in the center of this. So if either one of them actually acts non-trivially, then actually X is isomorphic to this. So this is the G module, and this is the GLN plus 1 module. So this is the same that we got for uniformly bounded modules. So the actions here and then here and here also look the same, but then as I said, there were two copies of A there. So this acts by this scalar that is coming is from here actually. There exists a non-zero, this pair is not, both cannot be 0. So then it is like this actually. So this is the action. Then what about the case actually when both of them acts trivially? So again we have this irreducible module where X is irreducible uniformly bounded. So if both of them acts trivially, then one can show that the t to the power m, that means that an plus 1 as well as this m plus 1 act trivially. So finally you are getting to a module again over the uniformly bounded module over the full toroidal tau n in n variables, because the two copies of an are vanishing. So this is the notation I use. So this 0 0 stands for that a and b are at 0 because k naught and d naught act trivially on X. Okay. So now as I said actually, so this I have given a sufficient necessary condition for this to be a Harishchandra modules. Still I don't know, like when I take this module and take the induced module and take the irreducible quotient, whether I get finite dimensional weight spaces, and even if I take this module and take the induced module and take irreducible quotient, whether I shall get finite dimensional weight spaces, we still don't know. But then really the result of Billig and Berman and Billig really helps us, which says that Lx is a Harishchandra module, that means it has finite dimensional weight spaces if X is an irreducible uniformly bounded and something called a polynomial module. So I am not going into the definition of polynomial module over this. And we could check that these modules that we got in this as well as the previous part are all irreducible uniformly bounded polynomial modules, and thus when you do induce and take the irreducible quotient, we always get an irreducible Harishchandra module. So the specification is essentially complete in this case. So the final results are like, if you take an irreducible Harishchandra module over this full toroidal, then it is either a uniformly bounded or highest weight type module, and if it is uniformly bounded, then it is like this, the uniformly bounded modules that I described. So again, lambda 1 is non-zero, and the uniformly bounded modules over the width algebra, and the highest weight type module that I just described actually. Okay. And this is actually, there was a conjecture made by Rao in 2004. He conjectured that all the irreducible Harishchandra modules over the higher dimensional Virasoro algebra has to come from the Sen-Larsen modules or the highest weight type modules up to a twist of an automorphism, and this is in fact the higher dimensional analog of the conjecture made by Katz in relation to the Virasoro algebra. And so that is one of the applications of our results, that we proved the conjecture completely, that it's, if you start with an irreducible Harishchandra module over the Virasoro, higher dimensional Virasoro, then it is either a uniformly bounded or a highest weight type module. If it is uniformly bounded, to then V is isomorphic to a uniformly bounded irreducible module over Wn plus 1, and the highest weight type module is like this that I just described. So here you note that there is no dominant integral weight of G because there is no G in Vir. Okay. So I think I will stop here. Thank you for your attention.
If there are any questions, we can have them.
So, are these results hold good for affine Lie algebra? You have used more than one variable.
Yeah. Affine also, yeah. But affine it is far more easier because these like the highest weight type modules are really easy to see. Highest weight modules, you don't face this problem of this induced module will have infinite dimensional weight spaces and things. So things are much more easier there.
No, but someone has done it?
Yeah. That's one variable case it's done.
Okay.
Yes. Yeah.
So are there any analogous development for Hamiltonian subalgebra?
Yeah, there is. So while algebra there is lot of things, so yeah, but Hamiltonian algebra, like I only look on the Laurent polynomial algebra, so there are some Hamiltonian vector fields. Okay, so there, like the results I showed for Rao for the Journal of Algebra paper where he investigated those irreducibility for those modules, Sen-Larsen modules. So there is a similar paper like that for Hamiltonian. Okay. And there are other related papers also, but still the classification is still open. It is not complete classification of irreducible Harishchandra modules over Hamiltonian. Yeah.
Okay, you suggested a paper of Rao.
Yes, there is a Journal of Algebra 1996 paper. Yeah.
And that Hamiltonian.
Hamiltonian, there is a paper by Billig student Talboom, Talbwm. So you can look at it.
Yes, correct me if I'm wrong.
Yes.
For the Virasoro algebra in one variable, there was this problem for a while of classifying the unitary highest weight modules, although I suppose this assumes a real structure on the algebra.
Yeah.
This exists. So does this arise here, and is it possible?
Yeah, that was very natural. I also asked the same question, that unitary representations, does it arise here? But here actually in my work it doesn't arise at all. But in unitary representations, like as I said, Matthew proved the conjecture. Before that, actually the unitary representations for the Virasoro were for Virasoro. No, Virasoro were classified by Chari and Presley in 1988.
Okay. But in this case, the same problem arises, I suppose.
Same problem means?
Arises. Looking at
looking at unitary. Yeah. When I solved this problem, I did in the general. I didn't go for the unitary case at all. Actually.
You didn't look at it.
No, I didn't look at it.
You can see what the Hermitian modules are, I suppose.
What are they? Sorry.
If you have an isomorphism theorem, you can see what the Hermitian.
Hermitian. Yeah. That's a good direction. I was also asking Rao about, but yeah, as of now I don't have much insight into it. Thanks for the question.
Any more question? Let's thank the speaker again. There is a talk at 6